Hello, everybody. Welcome back to the first technical talk after the break. I hope you had a great networking break and you managed to meet a lot of new people. It seems that there were a lot of people on the tables, so yeah, I hope it was interesting for you. And the talks so far have been very interesting. Uh, so we have a great talk about an open source tool, Scapy, here, which will be presented by Dr. Nils Weiss. Unfortunately, Dr. Weiss has had a personal emergency a couple of minutes ago, and he's unable to make it to the talk right now. So he has um, asked us to use the recording. And if he's available later during the conference, we'll make an announcement for that so you can meet him during in the networking lounge. Uh, so hold your questions till that. We will make an announcement if he joins, if he's able to join. Um, but yeah, um, yeah, we'll start the talk right now.
Welcome to my talk, Automotive Network Scans with Scapy. My name is Nils Weiss. I received a PhD in the field of automotive security. Before that, I did a lot of work with electronics and I got a electronic technician's education. And recently, I co-founded the Dissector GmbH. This talk is basically a continuation of our 2019 Troopers talk, where we introduced all the basic protocols for automotive penetration testing with Scapy. So if you're interested in the background of automotive protocols, watch this talk on YouTube. The agenda for today is a short introduction, then some information about automotive protocol stacks, the automotive protocols that we are covering in this talk, basically UDS, where we also give a small introduction. Then we introduce system states, we introduce stateful scanners and stateful fuzzers, and finally we talk a little bit about the obstacles for this work. The Dissector GmbH, if you're interested, has three major fields of operation. We do services and research, we do penetration tests of wireless systems, of automotive networks, of hardware security systems, and we do processor security. We also do trainings and offer trainings for applied automotive hacking and embedded systems security with a lot of hands-on experience. And we create security tools to automate penetration testing of automotive systems. So why did we work with Scapy, or do we work with Scapy at all? This plot here shows the number of commits for a couple of tools over the last years. And as you can see, the blue and the green line, these are two projects which received a lot of contributions over the last 19 years. For me, it was important to put effort into an open source project which is alive, and therefore I checked the vitality of the project by the number of contributions over the last years. Besides Scapy, there's also Metasploit, which receives even more contributions, but for automotive network tasks, the the design of Metasploit is not ideal, since it's based on web requests mainly, and this is somewhat too slow for automotive network communication. But Scapy was a perfect fit, and it's a project which is alive, which receives contributions regularly, so it was a good choice to put effort in order to have a Swiss Army knife for automotive penetration testing. Some acknowledgements here for the maintainers, for example, and for the author of Scapy, Philippe Bondi, and to Guillaume, Gabriel, and Pierre. Today, so this is the automotive protocol stack that we have implemented in Scapy to get an overview about the different protocols. We are talking about UDS today, and UDS can be on top of Ethernet-based and CAN-based communication. On CAN-based communication, we need the transport layer ISOTP, And on Ethernet-based communication, we need a transport layer, UDP and TCP, of course, but also diagnostic over IP or HSFZ. UDS was originated from KBP 2000, and it's an application layer protocol. As I said, we use diagnostic over CAN or diagnostic over IP for transportation. And the use cases of UDS are the configuration of the ECUs, the execution of test routines, software updates, information retrieval, or reading of diagnostic trouble codes. The vehicle acts as a server and the computer acts as a tester client. The communication is always driven by the client, and the communication is request-response driven. Here's an example of a request and a response. 2203E8, for example, is a read data by identifier, and response is 6203E8, and the data payload is coffee in this example. In UDS, we have three types of responses, either positive responses. In the first example, we see the 22 and the 62 as a service identifier. Negative responses, which is the 22 and the 7F. 7F is the negative response code. Or negative responses and then followed by a positive response, which is a way that the ECU can delay the positive response. So the negative response code 7.8 means request correctly received, response pending, and a little bit later we're gonna receive a positive response with our desired information. Why is stateful scanning necessary? Here's an example about a scan of three different states, and as you can see, in order to get information about the ECU, we need to take care about the state. And as you can see here in the negative response codes, only in certain states, certain services are supported. So for example, in session 1, we have a service called security access, which is where we get the negative response, service not supported in active session. If we change the session to session 2, for example, or to session 3, we receive incorrect message length or invalid format. But this is a negative response code which tells us that the service is implemented and supported in the session. We only crafted our request wrong, but this is by design in this phase of the scanner, since we are sending malformed requests basically to enumerate over negative response codes. Here's another example where we, for example, have the service read memo by address as an example, which is not supported in the session 2. But if we switch to session 3 in this ECU on the right side, we get a negative response code, incorrect message length or invalid format. And this, for example, for a penetration tester or a security researcher is pure gold, because if you find the read memo by address job, you can usually leak very sensitive information from the ECU. Another important or interesting fact is the response time of an ECU. Here you see two different sessions, and the response time changes by an order of 10, depending if we are in session 2 or in session 3. As you can see, for example, in the first line, the average answer time for a negative response. A negative response is a good comparison here, because a negative response always consists out of 3 bytes, which means the time on a CAN bus is always the same. So to summarize my thoughts here, depending on the state, the round trip time for an ECU to answer is different. The reason is we may run entirely different firmwares, either in the bootloader or in the application, and this depends on the state. So stateful scanning is important in order to identify critical services and functionalities. From the definition of UDS and of GMLAN here in this example, we can identify a couple of services which are defined to change the state of an ECU. For example, diagnostic session control or security access or ECU reset, communication control and routine control are examples. and tester present. So the standard already tells us which services change the system state. Besides that, we also have OEM proprietary sessions, for example. So these are some examples where an OEM introduced, for example, the coding session or the HDD download session and so on. Security access is another example, and we categorized four major kinds of security access that we see in automotive. Either very simple arithmetic operations where the key is not the seed, or mathematical operations where the seed is multiplied and added by some secret numbers and then XORed with other parts. Or we have proprietary XOR shift loops, which are sometimes implemented, where we have some kind of secret machine that creates us a key out of a seed. And we can have real cryptographic operations in some very modern ECUs where we have, for example, RSA signatures. So these are the four categories of security access I wanted to mention here to give you an overview. Another thing where we have a lot of states in the ECU is the software update process. The software update process is also defined in the ISO or in the ISO 14229, basically in the UDS standard. And it follows always the same procedure in automotive ECUs, at least in embedded automotive ECUs. And every of this state here is usually encoded in the firmware as a specific system state. So we have a state machine in the background implemented, and we need to follow the right order of commands in order to do a successful software update, which means as a researcher, we need to respect the system states in order to perform any tests on our software update. So this is another example where we have a lot of hidden system states and where we as a researcher need to be aware of system states. Now I want to give you one example, what you need to do, a quick example, if you don't have enough documentation. Let's see, we have a definition here about a couple of read data by identifiers and a couple of hidden states in the diagnostic set tree. There might be an OEM which implements something called active session state, and this is a more fine granular system state. For example, system state could be DTC, diagnostic trouble codes off, or flash mode activated or flash mode exit. And we had this, so this is a real world example of our research. We wanted to enter the bootloader, and as you can see here, this is a couple of cheater slides. I'm gonna jump quickly to the relevant section. So we want to enter the bootloader, and we have the desired session is equal to, so this is basically our programming mode, and this means here the extended diagnostics session state, which I previously introduced, is checked to be not 83 and not 84. Otherwise, we cannot enter the bootloader in this ECU. But we want to enter the bootloader for research, so we need to figure out a way how to bring the ECU into the desired state so that we can actually enter the bootloader. And we can do this by reverse engineering, but this takes a lot of time, or we can do this automatically with our scanner that I will now introduce. So to summarize what I quickly introduced, we have a protocol definition which can leak states. The round trip time of request and response can leak states. We can get stateful information or state information of an ECU by reverse engineering, either from the firmwares of a repair shop tester or by extracted firmwares. Or sometimes we figure out that there are read data by identifiers which change their values depending on state changes. But this needs a lot of observation and testing. So if we model this for an automated scan, we can see it this way, that we have a request and a response. And request and response together can be defined as node or as state. And the request will be our transition function, or basically our edge into the state. So this gives us all what we need in order to define a graph or a system state machine as a directed graph with the following definitions, which are, yeah, you can read it later. It will not bore you with this mathematics stuff here. This is how it looks like in practice. We have a system state machine here of two different ECUs that we analyzed as an example. We always start in the default state, which is the reset state of the ECU, and then with certain commands, diagnostic session control, for example, or security access, we can enter different states. And this brings us into different unique states of the ECU, and we can model this as a graph. And if we have this graph, we have the transition functions to traverse in the graph, and we can execute scans in specific states. In our implementation, we defined the protocol, which is the packet class, which defines a node. We have a test case, which generates requests, so basically packets, and which evaluates the response. And if it finds state changes, it will generate edges as transition function. And finally, in our implementation, we have an executor which stores nodes and edges in a graph. It can toggle the reset of an ECU, and it can modify the target ECU state according to the path in the graph. To implement this, to give you a quick example, we can extend our Scapy packets with a decorator. So here we have the UDS write data by identifier modify ECU state decorator, which we can give to the packet. So whenever we receive a write data by identifier packet, this will tell our scanner that this packet modifies the ECU state if the data identifier is, for example, F15A, which is a fingerprint. And the state is basically the hash of the fingerprint. Now we can write a fingerprint scanner that checks if a certain fingerprint is, or if the function of a fingerprint is supported. We just need to derive from our main scanner classes that were already implemented in Scapy, and we need to implement the function getInitialRequests, which is just a generator function to return a list of packets that should be tested. And whenever such a request is now sent to the ECU and a response is received, the scanner directly knows that the response can have a system state since we extended the response with the decorator. And this brings this class, this test case, into the position of generating edges. And finally, we can run this special fingerprint test in our executor. We just need to recreate an ISOTP socket here in this example. Also, a diagnostic over IP socket would be possible. And then we can run our scanner with a socket, with a reset handler function, and with a list of test cases. We can even give special parameters to our test cases here. If we want to fuzz the same thing in Scapy, we just need to change the getInitialRequest function in order to return random data, for example. This is all we need to do, and then we can start fuzzing random data in our Scapy system state-based UDS scanner. This is how the results look like on a real world ECU. All the green states are basically states where we were successfully entering the bootloader. The green states are states that are basically in the middle way. So this is a very, let's say, small example where the search space is very limited. If we look to a bigger example, it can look like this with a lot of red states, a lot of blues, a lot of yellow states, which we can almost not see, but also some green states here. So our scanner was successfully finding um, the entry into the bootloader in a bigger search space. We can go closer, how it looks like. Here are some of our green states. Oh, looks like spaghetti. And even a little bit closer, looks even more like spaghetti. So as we can see here, diagnostic session control is set to 2 in the screen states, and all the other states we have diagnostic session control 1 or diagnostic session control 3 and so on. So these are not the bootloader states. So we were successfully entering the bootloader with our automated scanner. Things that could affect the scan, of course, are the number of enumerators. If you have more enumerators, the scan can take way longer since every combination needs to be tested, and this means we have an exponential increase of our scan duration. The reset time might be a bottleneck, so some ECUs take 1 to 5 seconds to boot up, which we need to take into account since we reset our ECUs very often. We need some delays, might be a problem. After a session change, some ECUs need special delays since they need to reboot into a different firmware or a different section in the memory. Um, and the order of our passes might be a thing that affects the speed of the scan. So we can have a deep first scan, for example, or a random scan. There are different ways to play around and to optimize if you have a specific ECU. In general, there are some problems. The general problem is the lack of information. So after entering a new diagnostic session, what is the current level of security access, for example? Some ECUs might report information with read data by identifiers. Sometimes you can have hidden states. An example is some ECUs only allow a programming session if energy mode is not in power saving mode, but energy mode is not part of the UDS standard, so it's a proprietary thing here. And this is a hidden information or OEM specific information. Also state aliasing, aliasing is a problem. So our scanner could detect 2 different states maybe by our definition, but actually in the ECU it might be the same equivalent, and therefore our graph gets more complex. You can find this documented online, and now I will just quickly give this link here. If you're interested in our software, register for a free demo version as soon we have our software ready. You can download it here if you register, or we can send you a download link. Yeah, and that's it from my side. Here are the references of the talk, and thanks for your attention.
Great. So, like I said, Dr. Weiss is now actually available in person. So, if anybody has any questions, um, please ask them in the Q&A tab. Um, I think some of I think some of you did mention that uh, you were not able to get the audio of the recording because it was a bit low. So we will repost a better version after the conference. Sorry about that, but so if you have any questions, please do ask them. If not, maybe I can start off. So Niels, one thing that I want that I was curious about is so there have been a lot of attacks that have been sort of published on UDS lately. So, for example, at a recent SCAR, there was this attack on sort of abusing the random number to brute force the UDS authentication mechanism. Are things like that
Mhm.
built into, or like are more recent academic attacks sort of built into this framework, or can they be added into the framework of Scapy?
Yes. So of course, our framework is extremely extendable, and this is just, let's say, a test case for our automated setup, and we can easily test these academic attacks, for example. But as far as I understand, these kind of attacks, let's say more recent ECUs and more premium ECUs, have security access mechanisms which are far away from being brute forceable, like proper cryptographic schemes with RSA and things like that. So it's all possible, and it might be a thing for, let's say, lower priced ECUs, definitely. But so this is something you can automate, and also here it's very important to respect the state, since I said you might enter the bootloader, and the bootloader might have a different security access implementation actually. So you might trigger the bug in the bootloader, and you cannot find the bug in the normal application firmware.
Great. And if
Yeah.
people were to add this, so they can just contribute to the open source, I mean, if suppose somebody
Yes,
might
absolutely. So the slides here that I showed is all open source software. There's a huge code base in Scapy on this UDS scanner, and this can be extended, can be modified, can be taken as it is. Yeah, so everything can be used for free.
Okay, great. So we have one question coming in from the audience. So Venkatesh has asked, so are there any open source emulators for UDS that can be used with Scapy? And can you name some of them that can be used?
So what I use in Scapy to emulate UDS, so basically to act as a ECU, as a server, I'm using Scapy itself. So this is what I use in unit testing. There is like a concept called answering machine in Scapy, which you can basically use to prepare some responses basically, and whenever a request comes in, the proper response gets picked up and gets sent out. So a simple answering machine, and this is already part of Scapy for years basically. It's used for DHCP, for example, to build up your own DHCP server. It's the same concept, but I'm using it to basically test my own scanners in continuous integration environments. Does this answer your question?
I guess so Venkatesh, does this answer your question? Do you want to host or okay?
Okay.
We see a thumbs up, so I guess yes.
Yes. So if you want to learn more about it, you can basically take a look at my unit tests for this scanners. So there's a huge unit test directory in Scapy where I have unit tests for all the scanners, and basically in this unit tests I'm setting up a virtual machine, a virtual ECU that I use for testing.
Great. Okay, so we have no more questions from the audience. So just to sort of reiterate, will you be available in the networking lounge to answer any additional questions that people might have?
Maybe. I cannot. Like, I will be here for a couple of minutes more. Yeah, if people have questions and the network. So yeah, a couple of more minutes I'm available, definitely.
Okay. So yeah, so to the audience, there is. Okay, people have asked if you can provide the links in the chat. If you can
1
provide the
second.
links to the presentation from the chat. So actually, the chat from the session will disappear after the session ends. So if you can
Okay.
if you can just message them to me, if you can just direct message them to me, I will post it as a broadcast message, which doesn't
Yes.
disappear in the feed.
It's
So that way,
basically so the slides are a subset of the slides of my Troopers talk actually, and there is a link on scapy.net where basically this presentation is hosted. I post it here quickly. This is not the answer. I also post it here. So these are, let's say, this is a superset of the slides that I showed today because I had more time doing this talk. And in this talk, you will also find all the links.
so just for the audience benefit, I'm adding this in the main event feed. So if you need to access this link, it's been added in the main event feed, so you can access it there once the session closes. Um, okay, thank you everybody for attending. We will be starting our next talk soon. And Dr. Weiss, there's a dedicated table in the networking lounge with which is marked as for stage
Okay,
one. So,
perfect.
audience, if you want to ask questions, please meet Nils there.
Okay, see you.
Thank you, everybody, for attending.
Bye bye.